I will assume so. I don't know if you can hear. All right. Okay. Yeah. Thank you for inviting me to give a talk. And for today, I will present my recent work in the domain of generative AI, especially applied to medical imaging. So briefly about myself, I'm currently in the Division of Nephrology with focus on AI in quantitative health. So I attend my bachelor's degree in electronics and information engineering from Suzhou University, China in 2014. After that, I did like 5 years at the University of Iowa, focused on applied mathematics and electrical and computer engineering. Then I did 3 years of postdoctoral training, focused on deep learning for medical imaging at Stanford. I joined UF as an assistant professor starting from July of 2022. My research focus is mainly focused on AI in medical imaging. I have experience working with imaging modalities such as CT, MRI, ultrasound, PET SPECT, and pathology images. In terms of diseases, I've been focusing on lung cancer, prostate cancer, and aortic diseases. And in terms of image analysis tasks, the main focus will be image registration, where we align 2 images or multiple images into the same coordinate system to track motion, estimate deformations, etc., and image segmentations like organ segmentation, disease detection, and classification, classification of different stages of the disease, image enhancement, for example, image resolution and image denoising, image to image translation. Whenever you don't have an image modality and you would like to generate another image modality from, say, you convert a CT to an MRI when MRI is not possible for a patient. But for today, we'll focus on generative AI. And in terms of generative AI, I have experience with dealing with diffusion models, and those models are becoming current to-go method for most of, say, text to video generation tasks you probably already have experience with. And or more recently, like a flow match method, it just think about the generation process from a different geometric perspective. And more recently, like the vision language models, which allows you to not focus on one specific modality or specific task, but those type of models are usually can handle multiple tasks within one model, so that your model is more versatile and more generalizable. I found that AI agents have experience dealing with agents in the domain so that interact with humans purely based on natural language interactions, and the model can provide feedback purely based on instructions by the human and give exact information that the human needs. Oh, by the way, feel free to interrupt me if you have any questions. So it's nice to have this type of more interactive discussion. For today, because of time constraint, I am not able to cover everything I did in general AI, but I will focus on 4 different papers studies. Divided into 2 categories. One is diffusion models for medical imaging. Another is medical vision language models I have developed. Diffusion models, you think about it as a class of general models where you perturb or apply a deterministic, predefined process to progressively add noise to a clean data until it becomes pure noise. And the goal to train a diffusion model is to train a denoiser, which is parameterized by a neural network, to progressively reverse this forward process. That means that you start with the noise, and the learned denoiser is able to gradually remove noise from the data until it becomes a purely clean image. So the advantage of this model compared to previous generative AI models is that it can generate really high quality, high resolution images. And the training is very stable, although previously there are methods such as general accelerator networks can generate high quality images, but it's very well known for unstable training. So diffusion models has a very simple training loss. The training is pretty simple and stable, and it has a broad mode coverage. That means, yeah.
Shao, I don't know if you prefer that we ask questions in the middle or at the end.
In the middle.
In the middle.
Yeah.
So for this, you have 2 different images. What would be? You go from the first image to the second one. It was just an example because there are 2 different images.
Oh yeah, that's on purpose.
The noise.
Yeah. So basically, the goal of diffusion models is to generate new images for at least for the initial setup. is to generate new images. During the training, you have a very large set of like high quality images.
Okay.
You use for training, and you don't know the underlying probability distribution of this data. The goal of diffusion models is to learn such a distribution. Once you have learned such a distribution, you can easily sample new data that follows that distribution, which means that images will look similar to the images in your trained data set, but they're different. Yeah, you think about it like you have a very simple Gaussian distribution, and you have like observations at different time points, right? And you would like to learn a new like model that fit that distribution and allows you to generate new data samples, observations.
Predictive, but yeah.
Yeah. But your point is good, but because there's another way to exactly recover that high quality images using noise in a deterministic way. Yeah, there are multiple ways to do it. But initial purpose of this model is to generate new high quality images.
So is it denoising, or is it looking for the image and getting rid of the noise? Like, does it see the image in the noise, or is it gradually sort of determining what's noise and getting rid of the noise to be left with the image?
So the beauty of this process is everything is stochastic. It's a random process, which means that you give a noise, right? And you denoise, every time you can get a different image. So you think about it as that because the image is considered as a sample from a very high dimensional probability distribution. That every time you sample, like say you have Gaussian distribution, every time you sample, your sample will very likely be close to high density regions, but every time it's going to be different. The sampling process is stochastic. So this is the same thing. You start with the noise, you gradually denoise that noise, but you have no idea what the final image will look like. But you know that we're sitting in the high density regions. That's what we know.
Sorry. I have this follow-up question on that. So when I look at the last far right noise pictures, to me they look identical. What is the let's say we don't know what the actual picture is supposed to look like, and the AI denoises it. What is the guarantee that actually it's pulling out the right image and not something that is randomly created? Right.
Okay, so that talks about like conditional generation or unconditional generation, right? You can have some conditional generation that I only want cats of certain color, certain breed. Like you can describe whatever you want, and then you can use that as guidance to let your model generate exactly what you want.
But in with human imaging, we don't always get the picture that we want. We get what the patient has, right?
That's a good point. So that means I don't focus on unconditional generation. I only focus on unconditional generation. For example, I let the model to super resolve the image for me, denoise the image for me, not like a random generation, because it's not very useful in medical imaging. That's a good point, actually. Right, there's no more questions. This is scary, but basically, the idea of the reason why diffusion model works is that it's not a one step from noise to data. It uses hundreds to thousand time steps to gradually add noise and denoise. So which means that you have to pass your data through the network, say 1,000 times before you even get a good image generation. That's so slow compared to previous methods. They only have one pass. So this is now 1,000. So this is not going to work for clinical usage. So that's the one drawback of diffusion models, is that it takes thousands of time steps to generate data, and also the training is so slow. Like say, train a 3D model can take a month. So it's so slow to train and so slow to store. So my goal is to fix those issues. I would definitely skip those math, but the idea is that this forward steps of adding noise can be predefined. The user can define whatever it is, as long as it fits as long as it's gradually becoming noise. And that's about it. What we call a noise schedule. You can define that schedule. And once the schedule is defined, actually you can think about this as a stochastic differential equation. It's a differential equation, but you have a stochastic term, which means that none of your observations are going to be fixed. There's no way to know what exactly the observations are, but you know the distribution of the observations. So all those XT are intermediate Gaussian distributions instead of fixed observations. So That's like stochastic differential equations. But those equations are already predefined by the noise schedule. A user can predefine. You can define that process. But the beauty of this is that because we don't care about the forward process, we care about backward process that allows us to generate clean data from pure noise. So a theory from 1982 tells us that the reverse process is also a stochastic process, that you can solve this stochastic process by estimating the score function. A score function, think about it as gradient. So a gradient allows you to go from like a low density region to high density regions. Think about like you climb a hill, the gradient is the steepest like direction where you locally you go from low height to high height. But this is the same thing. So to estimate this, it turned out to be very simple, like L1 or L2 loss function. So this is a really simple loss, and that's why training diffusion models is so efficient and so stable. But I'll skip those. And basically, what we know is that we train a neural network to estimate the score function. And once you have that, you can solve this. Once again, and then you can solve this equation backwards. That allows you to every time you sample a random noise, and then solving this equation backwards, actually, you can finally get a clean image. And that's why there's some randomness to allow you to generate data, because this sampling process is random, and every time you generate a new random high quality image by solving the equation.
The noise is also generated randomly.
Yeah, noise is random sample from a prior distribution, say a standard Gaussian distribution.
So it is based on the distribution, or is it just picks a random?
So as a user, you can define what we call it. This is called a prior distribution. As a user, like the easiest way is to convert image gradually into a standard Gaussian. There's one way to do it, but there's multiple ways to do it. But this is the most popular way because that's the easiest. Like standard Gaussian distribution is the easiest.
So if this is a stochastic process, is there, let's say you want the image of the cat, is there a way that you're gonna get an image of a dog sometimes? Because it.
So here's the thing: if you train images, if you train a model based on images of cats and dogs, and you don't have any constraints in your like denoising process, you're gonna have images, random images, dogs, cats. Yes, that's gonna happen. That's why people start to investigate like conditional generation. So you give a condition. So your condition can be posed by class label, can be imposed by say a textual description. So you have multiple ways to let the model know I only want image of cats. Yes, the model can only generate the image of cats of specific color, specific type, whatever. You can have as many constraints as you have.
So it does, in this model, does it go down all these different pathways and say this is wrong, and it goes down the other, or is it
doesn't
correcting itself each?
It doesn't go to a different path, but instead it goes through the path that allows you to generate the cat. So the condition image will affect this process, will affect the prediction of your gradients. So the gradients go to different directions, will generate different types of images. So so which means this denoising model can take your conditions to allow you to generate whatever type of images you want.
So that will change depending on your goal image.
Yeah, that depends on your condition.
Shao, that actually seems to be a common theme for our questions. That so let's say you are an expert in prostate cancer.
Yeah.
So you receive the CT scan and you want to see what lesion or where it is in the prostate. Ahead of time, you have told the model that this is a prostate, it's not a kidney. Right? That's what you say is conditional. Just like dogs and cats. That
you can think about that.
Dogs and cats.
Yeah,
don't go for a pig.
You can think about it, but as long as I will show some examples, you folks going to have a better idea how I'm going to use those conditions to help you with the generation process to make sure we're not generating random images for patients, right? Which is not useful. Yeah, but you can think about it that way. Yeah,
sure.
So I'll skip this. This is like too technical. Just basically like diffusion models are good, but they are computationally very expensive. So that's the problem we're gonna address in my research. So for example, compared to a previous GAN model, this on 0.05 minutes, but to compare diffusion models, you get 10 minutes apparently. You're sacrificing your time for higher quality. Just because you need to use 1,000 time steps. So my goal is that okay, for the training, like if we use 1 time steps, there are already some efficient samplers that propose to use less time steps during sampling. So I just go in this paper, we just go a little bit more aggressive. So why not just using exact the same time steps for both training and sampling? So we only use 5 to 10 time steps in this research. By aligning those time steps for training and sampling, it turned out that this is very effective. That increases the training speed by 3 times. The inference speed is about like 100 times. So this becomes more efficient. But meanwhile, it's still achieves state of art like the image high quality. So this is the magical because you achieve like 3 goals at the same time. People always talk about like you have some trade-off, but there's no trade-off in this in this work. You achieve the best sampling, training, and generation. And okay, so this is how I apply this technique to 3 different tasks validate this method. One is for like super resolution. So for example, when you acquire MRI because of time constraint, right? You can have a very high implant resolution, but you go to different locations, you may have a low through plane resolution. And the goal is to predict the slices missing between so that you can have like more like true 3D MRI instead of like a 2.5D MRI. So this is the predicted slices in between, which we call it multi-image resolution. Another task is like low dose CT denoising. Because radiation doses can damage your healthy tissues and also like take a bit longer. So people tend to use low dose, say like only 10% of the doses to scan a kind of a noisy CT image. And the goal is to convert this low dose CT into a normal high quality dose CT with only like 10% of the doses. Another task is image translation. So say I have a T2 weighted MRI of my brain and I want to generate a T1 weighted MRI of my brain to T2 weighted MRI brain, CT to MRI. So this is like 3 tasks I choose to validate this method. Yes, so just want to show you the results. So this is super resolution. You have previous slice of a prostate and then the next slice. And you want to predict the one in the center. So this is the ground truth. So the input to my model is this slice and this slice, and I want to predict the one in the center. And those are some previous methods, and this is the visual results of our method. Yeah. So you compare this one with all the rest of the predictions. I think our method visually looks the best. Close to what
biased.
I don't think it's biased like this one. not aligned, right? Apparently those 3 are not as far off. I think this one is as good. This one is close to what we are doing. This one is a little worse. But to make sure there's no bias, that we quantitatively like evaluate how close they are. So those are PSNR measures how the intensity distributions are aligned. SSIM measures how the structural like similarities they are. So we also compare the training time and the inference time. So basically, if you use the exact same training and inference time, you can have better results. But we didn't show that if you those models can continue to improve if you have more time, but it's just not worth it. It may have to take more than a week to complete. Yeah, this is the one example. And the next example is here, like you have a low dose CT. So here I just point to the region where you can see the fissure of the lung. So fissure is very important to divide the lung different lobes, and they are very important. And apparently in the low dose CT, there's no way to see the fissure there. So this is the normal dose, and those are so this is the input to a model, and the model wants to predict the normal dose CT. And I would say like this is not okay. Those are not there, and those 3 are better. So at least you can clearly see the fissure in your reconstructed images. And by the way, those are 2D images. This work is already done 1.5 years ago. Now, surprisingly, like we extend this to 3D. Actually, the image generation is better than the normal dose. To my eye, it's much better. So it's much sharper, like though it's sharper than even the normal dose. Anyway, the key is same thing that you can see how useful those AI models can recover the missing information in this low dose CT. So and also for this example, this is the input and this is the ground truth. You want to convert this T1 weighted MR into a T2 weighted MR, and those are the generations by different regions, and we highlight like this region. So I think our model is preserve the details. Like those are like a little bit smooth, I think, compared to the ground truth. And those are the intensities are shifted. So yeah, and based on all those numbers, that model achieves best while having a very good inference and training time.
So if you train your model on the prostate or the brain or something else, or the lung, I mean, the computer doesn't care that it's looking at it's just looking at a pattern. So can you use that do you have to train it to look at another image of the kidney?
Okay,
or
so for here, it's yes,
or
that's
is
a good
it
point.
specific for the cuts and
Those models are task specific. If you translate to a different task, it's not going to work because the model never seen images of kidney. So yeah, I think that's where you need to train a more like a foundation model to do modern tasks.
But when you also talked about if creating a T1 when you didn't, or creating one image when you didn't have it, that's sort of not independent. They're going to be the same sort of light, bright images independent of what you're studying. So would you need to train it on?
We do have a study like with another team that we kind of we were focusing on image to image generation translation that we use it for different like prostate, brain, kidney, so all types of like imaging protocols or different types of organs, and then we show that if we do that, the model is able to generalize, and you can make this more like a conditional generation, say one from T1 to T2, or maybe T1 to T1 row. Yeah, so the answer is that you can do it as long as you have the enough training data and you have the right architecture. So you just need to adapt this architecture a bit to allow you to have conditional generation and different tasks. All right. For the time, I'll probably skip this because this is too mathematical. But the idea is that the previous defined methods are optimal, are not optimal, because those forward processes are randomly defined. So for here, I'm thinking about more like geometrical perspective. So why not define the optimal forward path? In the sense that if you think about like the shortest distance between 2 points in the Euclidean space, it's a straight line, right? But if you go to a sphere, it's different, right? So this is more like the concept which that allows you to find the optimal distance between two different probability distributions. So I'll skip the math. I want to use the Fisher-Rho metric, and this is the equations that we derived represent the optimal like noise schedule. But the key, okay, so here like this is continuous generation, so probably help a bit. So basically, you apply noise to your high quality images. But for the generation process, you have this noisy conditioning image to gradually denoise this conditioning image to generate your high quality image. So this is like the image denoising task. So this noisy image is used as a condition to guide the generation process because you want the generated image look similar to this image, but just a higher quality version of this image. So this makes sure you're not generating some random images, but the images that directly based on this low quality image, just a higher quality version of it. Yeah. So basically, so this is what I just presented, but basically, like this idea can significantly improve the training speed by another five times, and the inference speed by another maybe 30 to 40%. But still having a better results. So that's the takeaway. So this method I think is currently what I see the best in the field of conditional image to image generation. All right. So next, we go switch to the medical vision language models. Those models allows you to do model learning and to handle multiple tasks at the same time. Just a brief introduction. What are vision language models? So vision language models are those models that they learn like shared representations across multiple modalities, specifically like images and text. So for here, I just give you one example of a pre-trained vision language model can do those multiple different tasks. You can ask questions about objects on the image. You can ask the model to segment the object on the image. You can also ask the model to perform image editing as well. So multiple tasks at the same time. So in terms of applying those models to medical imaging, you can think about it like image text retrieval. Say as a clinician, I found a case that I'm not very certain about. I would like to search in the database. Any similar cases previously has already been discussed. And augmented report generation, generate a structure like regulatory reports to save the radiologist's time. And also zero-shot disease detection, if I don't have any labels and I still want to detect any diseases from the images. So this will save a lot of like labeling effort. Test-guided image segmentation, say you can instruct the model, say segment the lung tumor for me, segment the kidney for me, and what's the size of the kidney. So you can ask all those questions and give all those instructions, all sitting in one model to handle all those tasks. And I think this domain all starts from a model called like CLIP, contrastive like language training. So the idea of CLIP is that you would like to detect objects in your image, but you do not want to do any manual labeling, right? And what CLIP does is that it downloads thousands of images from the internet, all with captions on it, right? You have image, they have a caption describe what objects on the image. And what they did is they train a image encoder and a text encoder. So basically those encoders, you think about them more like abstract like feature instructions to represent the image or text using a vector, flow value like a vector. And those vectors includes like semantic information on your images and your text. And the goal is to train those encoders to maximize the similarity between image and text that correspond to each other and minimize the difference if they're not corresponding to each other. Yeah, that's a pretty simple idea. You don't need any trained labels. You don't need any well-defined loss function. You just do contrast learning using those like large like a web based data set. So the strength of this is that you can do zero-shot learning. And once this is trained, it can be used to do image classification. Say now if you have an image of dog and an image of cat, you want to know what image is this about. All you have to do is that you extract features from all those images from this image, and you have like two input into a text encoder. One, this is the image of dog, this is the image of cat. So the one, if this image of dog, right, the similarity between the embeddings for this is the image of dog, it will have higher similarity between my image representation compared to this is the image of cat. So this is how you can do zero-shot, image classification with no trained labels. And you can apply those, this idea into the domain of medical imaging, where you have regular reports that already identified like several different diseases, showing up on the CT or MRI images, and you can use those for zero-shot disease detection applications. But the one problem is the large computational cost when you extend the. So initially, like those vision language models are developed for 2D images, but for medical imaging, most of the time it's 3D imaging. And you can see like the amount of computation will increase significantly if we extend from 2D to 3D. So the first work we did is to address this issue to develop a efficient like image encoder to allows you to extract useful features from those 3D imaging volumes while preserving the computational cost. So the idea is pretty simple, that you decompose a 3D convolution into 3 parallel 1D convolution in the X, Y, and Z directions. So this allows you to reduce your complexity from cubic to linear. So this is a significant reduction in the computation cost. And once you have that architecture, so basically you can use the CLIP architecture to have real reports for HCT, or we do contrast learning. So once you train a good text encoder and image encoder, actually you can detect multiple pathologies or diseases in a patient at the same time. So here I think we have 18 different diseases, or 30, I'm not really excited, but so many of them. So what you do is that you, for each disease, you input 2 text prompts into your text encoder. The disease is there or not there, right? And you compute the similarity between those representations and the image representations. And the one that has the disease, that this one will have a higher similarity. If the patient does not have disease, this one will have higher similarity. So this allows you to detect multiple different diseases at the same time. You just repeat this process for different diseases. So for here, yes, we have 18 different diseases of the lung identified by the radiologist. In the report for the training, we have about 50,000 pairs of CT and radial reports to train such a model. So once we have that, we apply the model using the method I previously described to detect 18 different diseases at the same time. So this number might not sound like very high, but you think about it, it's not just detect one disease. you detect 18 different diseases at the same time. You average across all those diseases. So the F1 score have a balance between the precision and recall, just to handle the the distribution issues in the images. I think many of them does not have disease, so that's the most balanced method. So the takeaway is that if I use a tiny version of a model, you can actually already outperform current state-of-the-art transformer-based model by 2% in your F1 score. If to achieve the same performance, our model is only 5.8 million parameters instead of like 100 million parameters. So this is a very efficient model. Build on top of that we extend this, we use this architecture to build a unified 3D mandible vision language model. 3D vision language models are those models that integrate volumetric imaging data and text data, natural text data, to jointly learn those spatial semantic understanding and reasoning about your image. So key capabilities, you can do like automated report generation from those 3 metal images and visual question answering. You can ask the model like, are there any diseases or any abnormalities on my image? Text guided 3D segmentation and localization. You can ask the model to segment a disease, segment an organ for you. To train such model, we first start with the clip model for contrast learning. Once we have that, actually we will fine tune a large language model. So because for the question answering, you need a large language model to generate the results for you. So what you do is that you actually need to, because large language models like ChatGPT has no idea what the medical images will look like, right? So what do? You need to train what we call an adapter or model projector to allows you to project the image embeddings, image features into a domain, a space that large language models can understand. So basically what you do is that you feed this output from the projector into combine with the user like prompt with the LLM. So LLM takes those 2 inputs and to answer questions based on the user request. Say generate reliable reports for me. What is the what view is this image I'm looking at? So you can have all those different types of questions and let the LLM to help you to answer, but definitely you need to fine tune the LLM. You cannot directly using a random LLM. You expect it to understand what is vision language models, right? So that's the fine tune part.
Is there any sort of science to know how big your training set has to be for different images, and does it depend on what you're doing, and how do you calculate that?
There are some experience we can borrow, but we cannot use it here. For example, to train the 2D vision language models, people use like hundreds of millions, but we only have 50,000 just because we don't have the data like in the domain. So I think that's the one of the bottleneck for the development of models in the domain. There are the largest open datasets, and there's only one of the 2 open datasets is 50,000. So I think that's the main bottleneck right now.
So especially for this visual learning model, how do you introduce the variables? So I think you currently are showing us the CT and MR images, which is a 2-dimensional, it's a contrast image of black to white. It's just one linear pattern. But especially if this one goes to like, let's say, some pathology or some other learning model, now you have this sort of the color spectrum coming in. And so if the number of variables are that many, does that make your training or data set requirement much larger?
Yes.
At that point?
Whenever you have new modality, then yeah, you're gonna have like a more trained data set. Well, here I didn't consider pathology because there are already so many foundation models on that domain, 2D models. So for here, I'm mainly focused on 3D models. I think I have like CT, MRI, and ultrasound. Those are the 3 majority. Yeah, but I agree with you. Whenever you have a new modality, one of the model work on it, you need like more and more trained sample. I think that's also the main bottleneck in field right now. Like we have limited data, so.
Sorry for another question. Can you go back a couple of slides? I just want to understand this table.
Yeah.
What does accuracy hold?
Your accuracy, what are the means? So you think about it in the most intuitive way is that for each disease, how many for each disease and for each testing dataset, has diseases or not, and the number of accurate predictions divided by the total number of samples.
62% we can predict. Okay.
You think about it as for
I
any disease.
understand. I just wanted to confirm.
Okay, sounds good. Yeah. All right. So basically, the goal is that we start with the contrast learning I described just to extract useful features from the images first. Once we have that, we did some changes to the original clip model that they require a large data set of positive and negative cases. For here, we only use pairs, so one positive, one negative. So because we have small data sets, this has to be showing a lot more stable. So it's contrast between a pair of images. And for the multi-modal projector, previously everybody used multi-layer perceptron. So we decided to use a slightly different one, what we call MLP mixer. So we mix the channel dimension and the spatial dimension, and it turned out to be a more effective approach. But yeah, I'll skip this. It's more technical. And this is more some details of how I fine tune a very large language model like ChatGPT, how I retrain it for my purpose. So basically, I use a parameter efficient fine tuning method called LoRa. It's called low rank adaptation. So the idea is that the parameters in your for your network are, you can think about it as matrices, and it's very high dimensional, say 10,000 by 10,000, lots of parameters, right? If you directly fine-tune those parameters, take a lot of gradients, space. So the idea is to use low-rank representations that you can divide a 4-rank image into 2 low-rank representations so that you have significantly less parameters to update. So this is how we make the fine-tuning a bit more parameter efficient. Those are some results. So basically, the idea is that if you have a large data set, let's say 2,000 dataset, say images or text in your dataset, and then if you find the exact match between your, so this is the image to image retrieval, meaning that you have text and you want to retrieve the corresponding images, how accurate you are to retrieve the exact image or top 5, top 10. So basically, the idea is that if you have a large data set, our model can be a lot more accurate than previous method. Okay, this is more interesting because that's no visual results. So this is the results from the visual question answering, and some open-ended questions, closed-ended questions. So open-ended questions means that you can have some free-form generation like ChatGPT. Closed-ended questions are more like multi-choice questions, predefined answers. So what is planned in this image is so this apparently is an axial plane. And what is lesion located? Right middle, cranial. So I'm not quite sure, but I think the previous method is far off. This is close. I don't think this is exact. Right? This is close. And what organ has mass lesion? So this is clear, like this liver, but this model made a mistake. But anyway, you can also ask other questions, which I'm not expert. Seems sometimes the mass lesion, adenocarcinoma, contrast. Okay, this is important because this is about what CT phase is there. So anyway, you can see I have a few different type of questions, random questions you can ask if you have.
And what's who is this designed for? Who's your end user here?
Well, here I'm thinking about clinicians, and also the training for education purposes, say clinical fellows, medical students may also use this one as a way to help you kind of for learning purposes, or maybe have another reference whenever they are unsure. But as we have seen, the main issue is the accuracy, right? The model is not as accurate just because we have a small training dataset. So my point is that if the field continue to grow, if we have more training dataset with expert annotated dataset, the model can become better and better in the future.
Is your denoising model being used? Because that I think would be really useful for some of the images and saving time and radiation to patients.
Okay, yeah, it has been used, but not in this task. I didn't have chance to present. I designed a AI agent that is more like an online web tool. That yes, you can ask the model to noise the image, ask the model to ask questions. The model can do everything, basically. That's what I do. And you combine all those models with LLM, and also using, for example, the long chain, long graph model to reason. So the model has the reasoning capability to interpret what the user wants and what tools I need to use and how do I connect all those answers and present it to the user.
So why isn't this being used for sort of every image in radiology? Because there's no perfect image. There's always some noise in the images that could be improved upon. So why isn't it using on every X-ray you get in the ICU or every MRI that has noise artifacts and getting rid of all of that?
I think in clinics they probably already have some commercial tools allow them to do some basic. No,
I don't think they
okay,
do.
but what I know is that low-dose CT has already been used in many institutions. Low-dose to normal-dose CT that has been applied.
How many images do we get back as artifact? Right, they can't read it. Especially MRI, that's really big. But also in the ICUs, the images are so bad half the time that this sort of thing I think would be valuable.
Yeah, I totally agree. So I think this is something I wish
at least
that forward.
For a university that is more apt for it, I think a beta version of this in a regular sort of as an assistance to radiologists would be helpful, right?
Or even non-radiologists may be more important, like in the ICU.
No, I think the non-radiologist, the problem is the legal perspective comes in. But at least for the radiologists, like they still are licensed people. For them to have this available to just say whether that makes sense or not with the accuracy of 62%, like I think something that cleans up the image or sort of gives a little perspective. I mean, at least what you're showing is advanced enough that it can be left to some clinician.
Because the endpoint could be how many times do you have to redo the study versus not redo the study.
Do you have a radiology colleague that
yeah,
collaborator
with Bruno Hochschauer from radiology department. We try to collect more data at UF.
Yeah, I think this is the biggest thing is getting more data because we don't want to give noise pulmonary edema, on accident or something more sudden, right? Some faint fibrosis from the lungs or something from the kidneys and punctate lesions that we just might not be able to. They are there and we can see it as clinicians.
Yeah,
but AI may see it as random. Machine noise.
Yeah, I would consider those more like general AI models. Right now, I would prefer a specialized AI models first, just because you have enough data to tackle a small problem. This is more like a future work, which you have enough data, then allows you to train a dual foundation model to handle everything.
So I think there are a lot of registry creation sort of IRBs. So IRBs do allow registry creation. And I think a beta version of, at least, I'm not sure about this labeling part yet, because I think there the accuracy is really lower. But at least that your denoising and noising part can be applied under a guise of a registry IRB for a day-to-day clinical practice, because then what you'll have is you'll have a much frequent application of your methods onto the clinical data set. And then the other way around, once they label everything for you to get back for your clips, you will get a full report of it. And so it becomes much easier for you to sort of connect as a registry, I'm assuming, a beta version.
Yeah. I wish to have some collaboration to enhance the images for the radiologist. Right. Okay. Let's skip those for. But this is what the model generates. So those. I like ChatGPT to highlight regions that make sense to align with the original report. But I talked to radiologist that, and he told me that this is not useful. So anyway. Yeah, it's just because the model made a lot of mistakes. Yeah. Which is reasonable because the model only have 50,000 examples. With for MRI and CT and different organs, I don't think the model can. But it's better than the previous ones, which totally is out of the.
My apologies, but so the 50,000 training images, when you say they are not enough, is it because the abdomen is a complex organ with multiple multiple different potential
It
organs?
covers every single disease and every so this is
So 50,000 is between head to bottom.
any disease, any
Oh
organ,
my.
any modality. The
Oh,
model
okay.
definitely cannot. If you focus on only one disease, might be able. Even for the one disease, the lung, 18 different diseases, the model has 62% of accuracy. Yeah, this is a very challenging task. So 50,000 definitely is not sufficient.
Gotcha.
But this is also promising because the model at least can have closer to the ground truth. Yeah, thank you. I don't have a chance to present more, but yeah.
This was
Okay, Shao, I think you asked all questions in the middle of your talk.
All right. Thank you very much.
Great.
Thank you.